Apatim, Simone, this is Eric. Can you hear me well?
Yes.
Yes.
Very good.
Okay.
I thought initially that Victoria would go first. I'm happy to go first. There is no problem, but I just want to make sure that
So Victoria is going first. So sorry for the confusion. Okay.
All right. Okay.
Thanks everyone, and thanks everyone for joining. And apologies for the glitch. We always expected this to happen. Welcome to the sixth GW Open Data Workshop. This is the second time that we are going in this hybrid mode. And this is mainly possible, this workshop has been really possible because of the contributions from the whole LIGO, Virgo, Kagra collaboration members. And you will meet some of them as mentors, both online and offline. And they're also some of us are the co-organizers who are also present in this call, like Simone, Agatha, and Greg Ashton. Just to explain how this meeting is going to happen, this meeting has it's mostly consisted of three parts. And let me share my screen. Yeah. So, right, if you can see my screen, so this is basically the landing page of the Open Data Workshop. So you go to this GWOSC, and from the workshops page, you can find the sixth Open Data Workshop web page. And I'm sure most of you have registered here, and we will have the initial lectures, which are going to be online, so which you can find here. And these lectures are either you can see them on Zoom, or you can watch the live stream on YouTube, and we will also make the video available on YouTube later. So today we will have a couple of lectures, one by Victoria Xu and the other by Eric. And apart from the lectures, we will have the tutorial sessions. So you can go to the from the online course, which is not here. Yeah, right. You can go to this ThinkFig page, and then if you click on the Open Data Workshop, you can go and find the entire course here. So you can go through all the sessions, the lectures and the tutorials, and once you complete this, you will be given a certificate. The other part is there will be, if you are joining an offline or in-person study hub, then there will be mentors who will help you go through the tutorials. Okay, so do appreciate the mentors who are going to help you out, because they are the reason why this workshop is happening. I think this is most of it that I want to tell you right now. And if any of the co-organizers want to say something, this might be a time.
Yes, sorry, Pratim. I think we need to make a co-host also Victoria Xu, because we haven't done it yet.
I thought I made that, but let me just check.
Yeah, probably you pick up the wrong person by mistake.
Oh, okay.
And in the meantime, let me also add that if you want to ask any question during the talk of our scientists, you can do it using the Ask Iguin forum, which you can find it here. Let me send the link to the general chat. So the first day questions can be posted here. And oh, just a second, sorry. Here, I put a link in the chat, and all the mentors will try to reply to your questions. So I think we are done, and maybe we can start with Victoria, right?
Sorry, this is the link for the question to the tutorials. There is another topic specific for the lectures.
Oh, sorry, apologies. Too many links.
And
Too many links.
yes, because I sent both link in the mail of the remark to the for the reminder of the meeting yesterday.
Okay, then this should be the correct one, right?
Yes, but they both
Thank
are
you.
indeed one for the lectures, one for the tutorials.
Okay, I think Agatha, you want to take it away, right? To introduce Victoria.
So I can do this. I think I was supposed to do this. Sorry. So about the ask.igwin, yes, I was going to say that. So for the lecture sessions, we have separate links for the lecture sessions as well as the tutorials where you can post your questions. So it's better that you post your questions in the respective links so that it doesn't get decluttered. And so you will find for every day there are links for the questions as well as for the tutorials. So now moving on to the main section of the first day. So we have the pleasure of Victoria Shu giving us the first talk, and she's a postdoctoral associate in the MIT LIGO group working on detector commissioning of the frequency-dependent squeezing upgrade in LIGO. So over to you, Victoria, whenever you want to start. You're welcome to start. Thanks.
Okay, that sounds great. Thanks for the introduction. And yeah, this is exciting to be able to share some of the LIGO detector technology with everybody here. So let me go ahead and share my screen. Let's see, can everybody see this okay? Okay.
Yes.
Great. Yeah, so it'll be hard for me to monitor the chat and the questions, but as they come up, you're welcome to, the organizers are welcome to ask them live. You're also welcome to wait till the end, either way. So, okay, let me just get started then. Yep, so this is the detector overview, and like Abraham said, I'm a postdoc at the MIT LIGO group. So LIGO is operated primarily by Caltech and MIT. So I'm working on detector commissioning, specifically of the new frequency-dependent squeezing system that we're adding to LIGO. And this is one of the big core upgrades for the next observing run 04 compared to the previous observing run from 2019 to 2020, which was the third observing run 03. So just to overview at the beginning of this workshop, let's see, what are gravitational waves? So gravitational waves are these sort of ripples in space-time. So kind of out in space, there are two dense, very, very dense objects that kind of orbit each other, get caught in each other's gravitational pull. And as the two objects kind of in spiral and merge into one final compact object, what happens is that energy is of them kind of orbiting, in spiraling, and merging, the change in mass is actually radiating gravitational radiation throughout the universe. And that's what we call gravitational waves, these ripples in space-time. So you can see an event like this comes through the Earth. And what we see on Earth is what we call a strain in space-time. That is, if I have a ruler that's at an upwards angle and then at a 90 degrees angle, so an upward and a rightward arm of my ruler, what I see is the differential change in length of the two arms of my ruler, of this L that the two rulers form. And this strain, this effect is of course extremely exaggerated. This strain is really a displacement for gravitational waves, even from really massive objects like tens of solar mass black holes. The strain that we're detecting with the LIGO detectors is of the order of 10 to the minus 19 meters over a total length of 4 kilometers. So the total strain is of the order 10 to the minus 21, which is just an incredibly small differential change in the two arms of this L. So let's see, so if we keep going then, there are the two LIGO detectors that run in the United States. One is in the upper east corner, in the northeastern corner of the United States in Washington State. That's the LIGO Hanford Observatory, and that's the one where I've been working at most of the time. And the other LIGO observatory is the one in Livingston, Louisiana, which is in the southeastern corner of the United States. So essentially, as far as you can get apart, that's where we've built the LIGO detectors in the US. But this is really a worldwide effort. So there's Geo 600 in Germany. There's Virgo in Pisa in Italy. There's Kagra and a mine in Japan. And coming online in the next decade will also be LIGO India. So this is becoming a really big worldwide so-called like network of gravitational wave observatories that we are building on Earth. And so how do we what's the premise of gravitational wave detection? It's really laser interferometry. So a laser shines into a beam splitter, gets split on two paths. As those two paths change with respect to one another, the amount of laser power at the output port, that's the brightness of the power at the output, changes as the two arms move. So what you see here is the light goes into the beam splitter, reflects off the mirror on one arm. That light comes back to meet itself at the beam splitter. The electric fields of these two lasers interfere constructively or destructively, depending on the difference in length in this L. And so this is sort of the premise of laser interferometry, is that as the arms change, the interference pattern changes. And what you see at the output of the interferometer on the screen here is the brightness of the light at the output is changing in response to the strain. That is the differential change of the arm length in the interferometer. So this is the sort of the premise of how a laser interferometer operates. Okay, if we keep moving on now, let's see, this is just giving you kind of a tour, maybe a real, in some sense, detector overview of the LIGO Hanford Observatory. So what you see here, LIGO Hanford in kind of the desert part of Eastern Washington, as you saw in the previous slide, a laser comes into a beam splitter. This beam splitter is sort of in the corner station over here. The laser comes into the beam splitter. It gets split amongst these two paths. That's the plus X arm and the plus Y arm. They form a sort of, this L shape of our detector. Light comes back from these 4-kilometer arms, interferes with the beam splitter in the corner station and the main lab spaces. The output photodetector then detects the power variation as the two arms move, for example, due to gravitational waves passing by. And so what you see when you look at the output, for example, current of this photodetector, is you see a strain signal like this, which is a change in the total power depending on how the gravitational waves strain this L. So this is a very high level detector overview. We can zoom in more to this. Really, LIGO is much more complicated of an instrument than sort of this simple picture of a laser interferometer, because given this very, very long arm, you sort of want to juice as much science as you can out of this. And that requires power recycling, signal recycling, and several other core optics that make our instrument more sensitive, even given its size. And so if you look inside this main building here, our main corner labs, this is what the inside of our lab spaces look like. That beam splitter I described to you earlier is in this sort of pile out here. The main laser is out over here on the right. So the main laser comes into the beam splitter and then gets split amongst the plus X and plus Y arms that we saw. So this is sort of the heart of the L of the LIGO interferometers that splits the beam to start with. If we keep going and we look inside of one of these big domes, what you see is, for example, the test masses are suspended on quadruple pendulums. And that's so, we're detecting this very minute change in the distances of this L. But that means that we have to be able to isolate the motion of all of our core optics from, for example, somebody walking by, wind, things like this. But that requires really phenomenal seismic isolation and mechanical isolation and acoustic isolation. So that's why LIGO is, it's one of the largest vacuum systems in the world. So there is no air inside of here except when humans go in to service and work on and upgrade the detectors, the real inside the heart of the detectors. And so you see here optics that are suspended from ground motion to try to suppress the effects of ground motion detectors. And here's just for scale, the size of the optics compared to the size of, for example, humans who go into the clean vacuum system to work on the optics and upgrade the optics. So this is sort of an interesting detector overview, that this is a very, very large and kind of phenomenally engineered detector that we run. And so this will be said a lot more, of course, as the workshop goes on, I'm sure, but the dawn of gravitational wave astrophysics sort of started in late 2015 with the first detection of gravitational waves with LIGO. And that was seeing two black holes, each of which are about 30 times the mass of our sun. At a distance of 1.3 billion light years, they inspiraled in about half a second, and during which in the course of that half a second of inspiraling, they radiated about 3 suns of energy as gravitational waves. And so this extremely dramatic event of like 2 black holes, 30 times the mass of our sun, produced an almost unobservable strain on Earth. Again, it's that strain of about a part in 10 to the minus 21. So this is an incredibly small signal that even, you know, our very well-engineered detector is right at the limit of being able to see. So this won the Nobel Prize in 2017. And just to give you a sense again of this sort of precision that we're talking about, a strain that is this L changing back and forth by 10 to the minus 21 on a baseline of 4 kilometers, that's detecting something move by a very small amount. That's approximately equivalent to detecting the distance between the sun and Proxima Centauri change by about the width of a hair. So this is a very, very precise measurement. And the distance that of the motion itself of our 4 mirrors that we're really detecting compared to the diameter of proton, we are sensing really displacements over 1,000 times less at times of compared to the diameter of a proton on a baseline of over 4 kilometers. And so how do we reach such like precision with a detector that we build? The key is kind of understanding the signal and understanding the noise, understanding the signals we're looking for astrophysically, and understanding what limits the detector noise, and are we at the fundamental physical limits of our detector noises. And so these are sort of the things we think about. So in terms of the gravitational wave signals, what you can see is that heavy black holes, the signals that they produce are often slower. They ring over seconds as they inspiral and merge, compared to, for example, binary neutron star systems, which are binary neutron stars are very light, order 1 to 5, maybe solar masses, versus black holes, which can be tens to, you know, nobody knows really how, I guess, big, but at least, you know, the supermassive black holes are millions to billions of solar masses. So you have black holes anywhere from 5 to 1 billion solar masses. Most of the ones in LIGO's detection band are about 100 or less, 200 or less solar masses. So these sorts of astrophysical gravitational wave sources, black hole mergers and neutron star mergers, produce very different signals, both in how low frequency black hole mergers are as they inspiral and merge, and how high amplitude they are as they finally merge and ring down, compared to neutron stars, which have a long pre-merger signal, and then accordingly a very high frequency post-merger ring down. And based on this, you see that where we want to improve our detector sensitivity is sort of over the seconds band, as well as this hundreds of hertz, as well as getting into the kilohertz band. All of it makes us more sensitive to different types of astrophysics. And so just for comparison, you can sort of see here what black hole events typically look like in terms of their strain and their frequencies versus binary neutron stars, which are small and zippy and have these fast light signals. And then, of course, the next piece of the puzzle is detector noise. So if you look at the noise in the first observing run, the first real observing run of advanced LIGO, where we detected gravitational waves, that's here in the light yellow. In the light gray. The second observing run, 02, that's here in the orange. The third observing run, 03, that was about a year long. And you can see how the noise between 01, 02, and 03 changed dramatically. And a big, that was also a big impact as well for our scientific detection rates. You can see in the total cumulative time of observing between 01 and 02, about a year, there were a total of less than 10 detections of gravitational waves. And since then, the total cumulative number of events increased dramatically as we entered the third observing run. That is, the slope of this line changed a lot to show that our detection rate itself really went up. And that was exactly a result of improving the detector sensitivities. Where the biggest improvements here, where you see the O3 noise curve really go ahead of the O1 and O2 noise curves, was increased laser power and the addition of quantum squeezing. These two were huge factors of increasing our overall sensitivity. And the way that we know how to improve our detectors over time and where to invest efforts in our technical sort of engineering and commissioning of the detectors is we look at the noise and we calculate what are the fundamental limits of our noise that we understand. That's all the solid lines you see down here. We also measure the total noise with as many external metrics as we can. There are lots of types of noises we can directly measure. So we measure all of those and understand how it relates to our total detector noise. And that's, for example, what you see here in the dark purple. And then so we compare our total measured noise, the red curve, with the sum of all the noises we know, for example, this dotted black curve. And together what that tells us is what types of noises can we fundamentally improve on, and what types of noises have we fundamentally reached our limits in terms of improving, and what are really the upgrades that will give us more astrophysics. And something you can see here is that across a huge part of the detection band, what limits us is quantum shot noise and quantum radiation pressure noise. And this quantum shot noise, we can reduce it by increasing laser power. We can also reduce it by injecting quantum squeezing. And the quantum radiation pressure here you see in orange is kind of the back action counterpart to improving on quantum shot noise. And in O4, we were able to inject frequency dependent squeezing now versus just the frequency independent regular squeezing that we used in O3. And that's one of the major upgrades for O4. And so you can see understanding what limits our detector sensitivities really drives us in terms of how we decide to upgrade detectors, and understanding which detector upgrades will be really impactful to our scientific outputs. So the next observing run, we're almost doubling the arm power, going to 400 kilowatts of circulating arm power in the arm cavities of LIGO. We're injecting 4.5 dB of frequency dependent squeezing that comes into the output port of the interferometer. And as well, we are improving our core optics along the way. And so you can sort of see here, just to spell this out again, between O1, O2, and O3, these improvements really dramatically improved and increased the amount of astrophysics we were able to do with the LIGO detectors. And I'll just say briefly here, quantum squeezing goes in through the output port of the interferometer. And there's the two components that are sort of tied together by Heisenberg uncertainty. There's the shot noise, which again is improved by increasing laser power and increasing squeezing. But then there's the back action component, this quantum radiation pressure noise that is tied to shot noise with Heisenberg uncertainty. And so usually with squeezing, you can improve one noise at the cost of the other, but it is sort of a balance. And something very exciting for O4 is that we are now able to play some fancy tricks and reduce shot noise and radiation pressure noise. And that's what you see in our recent measurements with squeezing, that compared to no squeezing, no injected squeezing at all in black, compared to the O3 style squeezing, that if we were to inject that into our LIGO detectors today, we would see this huge degradation of noise in a really important astrophysical band below a couple hundred hertz. With frequency dependent squeezing, which we've now commissioned for O4, we're able to undo kind of the detrimental back action that comes with squeezing. And so now we can preserve all the gains that we get from using quantum squeezing in the first place while increasing the total squeezing level in general. And so this is sort of an exciting upgrade for O4 that I've specifically been working on. And so for the rest of the talk, let me just show you a few pictures here of what it looks like to do on-site work in the LIGO detectors. So in late 2021, the squeezer from O3 was completely redone, upgraded, and moved into its own separate vacuum chamber house. That's what you see here. You see some of the new relay optics we've installed for the squeeze light path. And you see the input mirror to the long baseline filter cavity that we've installed. That's what allows us to sort of like basically avoid the back action noise from quantum radiation pressure. And so these optics were all largely new and recommissioned for the next observing run. And so you can also see these optics are in vacuum. So working on this is a large kind of clean room exercise. So in parallel with recommissioning the O3 squeezer, we also built up this new filter cavity, which is really a 300-meter in vacuum system, which required its own new beam tube enclosure, and the end mirror required its own new clean room with its own new building to house it. So here you see the construction of the new filter cavity beam tube in parallel with the interferometer's plus Y arm. It runs like this out of the lab building. This is both at LIGO Hanford as well as LIGO Livingston. And then you can see later on, this beam tube as well crosses through the centers of our lab. So in addition to the plus Y arm, you see here, the filter cavity beam tube runs in parallel. Here, it goes through the building you just saw being constructed late 2021. So yeah, this was a big infrastructure upgrade for the next observing run. And in late 2022, we got the first lights and locks at both LIGO observatories. So you can see a lot of on-site crews here looking at, this was the first time we were basically able to open up the entire filter cavity beam tube and take a look at locking the filter cavity. That was very exciting. And at Hanford, and then shortly after at Livingston, we saw the first signs of frequency-dependent squeezing in the full interferometer, which is very exciting. And since December 2022, now we are spring 2023, preparing imminently for the next observing run 04, which is slated to start in just a few weeks. Both sites have seen up to 4.5 dB of frequency-dependent squeezing. That was the set at 04 goal. And Livingston is in fact has seen over 5, almost 6 dB of squeezing, which is really amazing. And now we are also working on robustness and automation, so we can more or less run continuously with frequency-dependent squeezing in excess of, here it's quoted 18 hours, but that was already several months ago. So we've now been able to run with frequency-dependent squeezing for over 20 hours, almost 30 hours, with full automation and integration with the full interferometer. And going forward, this is an exciting demonstration of being able to preserve the gains from squeezing and reducing the black curve to this green-purple curve over here without facing the consequences here, where the green curve exceeds the black curve. And this frequency-dependent squeezing that we now have for 04 is very exciting. And of course, future detectors always dream up more ambitious goals, which is exciting to see. For example, in 04, we're not just beyond just doubling the laser power and adding more squeezing to reduce the high frequency detector noise, frequency dependent squeezing to reduce the low frequency detector noise. Next generation detectors, of which many conceptual designs are emerging now, want to see even more squeezing, even higher laser power, better coatings for the optics, and so on. So there are many upgrades in store to increase the sensitivity of future detectors quite dramatically. So let me just finish up here. This is just more on the detector overview front, what the LIGO Livingston control room looks like when you're sitting there working in this control room. Here's what the LIGO Hanford control room looks like. LIGO Hanford has funny problems, like, for example, tumbleweeds. It's just to say the LIGO sites are often in remote areas because that's better for seismic performance, all of this, but it sometimes means you get stuck in a tumbleweed storm. And this is the LIGO MIT group where I work. Unfortunately, I do not have a picture of the even larger Caltech group, but LIGO is a much bigger scientific collaboration than just MIT and Caltech as well. Over 1,200 members, over 100 institutions are involved in LIGO scientific collaboration, 18 countries. So this is a very international, large collaboration with much more than just detector commissioning required to see kind of the astrophysical success of this device. And with that, let me just finish up here and say thank you all, and I'm happy to take any questions. Thank you.
Thanks a lot, Victoria.
Thank you.
So we do have some time for questions. So anybody who wants to speak up, is it possible for you to raise your hands?
Maybe not. Oh, sorry, there are some drilling here. I wanted to say that there are some questions on the Ask Gwyn, so maybe we can pick one from there and ask Victoria.
That's great. Yep. I think I'm seeing a message.
I am seeing a message, so let me just read out to you. So there's a question which says that, do you think that we should consider building a futuristic mini GW observatory in the moon when it comes to economics and more precise measurements?
I think so. There are already proposals for this sort of project. And the proposals are very interesting, I think. I guess I would say, I don't know. I think that on the moon, you could reach a new frequency band for gravitational wave observatories. I think that's very exciting. In terms of the scientific output you could see from building the proposed moon detectors of gravitational waves, I think that they could unlock a scientifically new frequency band for gravitational wave detection that is very hard to touch on Earth, because on Earth, it's very hard to detect really much below 1050 hertz gravitational wave signals, just because the seismic noise is too great. So for example, for LISA, the space-based gravitational wave detector, that'll be amazing. They can unlock a very low millihertz frequency band for gravitational wave detection, which in terms of the scientific kind of signals you could detect, the astrophysical sources you could detect with gravitational waves in that frequency band. It's very exciting.
Yeah, right. So to add to that, I know of like there's this Italian group which wants to build a kind of a detector on the moon, which is called the Lunar Gravitational Wave Antenna, which basically focuses on the decihertz band.
Yes.
There are other such things like putting a LIGO kind of a detector on the moon and stuff. So yes, right. So there are a few other questions. Let me take that. What is quantum squeezing? A short overview would be great. Maybe a couple of lines if that's okay.
Yeah, quantum squeezing is essentially in some sense, it's almost like magic. You basically have a second laser that mimics the vacuum correlations of the main laser, and you basically make laser light at the same frequency as the interferometer laser using a totally separate laser source. But you kind of engineer it so that for every photon, you don't just get one photon at a time, you can instead get 2 photons at a time. And what that reduces is shot noise, because shot noise is fundamentally photon counting noise. So this way, if you know you're getting 1, you get 2, and that actually reduces the uncertainty in terms of the time of arrival photon counting shot noise. So quantum squeezing is essentially just a light source at the same frequency that you overlap with the main interferometer beam, but it has quantum correlations in how the photons are created in time. So it produces pairs of photon at a time rather than random productions of single photons, which is typically how a laser operates. So you're sort of playing this trick on the laser light that when it overlaps with the main light, it actually reduces the uncertainty in whether you're getting 1 or 2 photons, which reduces the counting noise. And that's one of the big manifestations of quantum noise in the interferometer.
Okay, thanks. So there's another question. Are the different detectors have exactly the same design apart from the different location? I can give you a question if that's fine. Apart from that, so okay, can you explain why there are spikes in the sensitivity curve, especially at higher frequencies?
Yeah. So the detectors, this generation of gravitational wave detectors are all the same operating principle in the sense that they're all an L. They're all a laser interferometer on the ground with beam tubes that close off air from like 2 perpendicular L-shaped arms. That's what's in common about all of this, the current operating facilities. What's different is how long these arms are. And even in Japan, another difference is that they're actually operating in a mine and running their mirrors cold to reduce the thermal noise that really limits in a really critical astrophysical part of the band around 100 to 500 hertz. So they're running cold to reduce, again, like looking at the noises, to reduce one of the most fundamental noises we fight with, which is thermal noise. They're running their detectors cold and underground as well to try to be, there's usually better seismic performance and the deeper you go into the ground. So they're hoping to improve on these two fundamental limitations of ground-based detectors, both colder mirrors as well as being underground. And so while they're the same conceptually, as in they're both Ls, they each have their own differences to them. And all the detectors are implemented with different seismic systems, different lasers potentially. So each detector has really come online in its own way, although they all share a basic core geometry to them. And then about why there are spikes in the detector noise curves, a lot of those spikes are a large majority of them are understood, I would say. They range from, for example, the test masses are suspended on these glass strings. Those strings, you can ring them up as if they're the string on a violin. And those are very, very narrow band, and they sustain a lot of oscillation. So those are often the very sharp features you see in the high frequencies. It's the kind of violin string modes of the suspensions that kind of hold the masses. You also see things like 60 hertz lines, and the harmonics of, in the US, at least 60 hertz is our power line. So you see 60, 120, 180, so on. Another thing you see is that there are a lot of lines we have for calibration, meaning we need to understand what the signal at the output interferometer of the interferometer looks like compared to a drive on the test masses. The way we do that is we shine a laser to move the test masses a little bit constantly, just a laser that's turning on and off, kind of around 450 hertz, 420 hertz. And we see how that motion looks like at the interferometer output. That allows us to hold, for example, some calibrations. So between calibration lines, injected lines that we use to characterize the interferometer different ways, known sources of ringing and so on. There's a lot of these lines are expected or injected for our characterization purposes.
Okay, thanks a lot. I think this is a good time to thank Victoria once again. And for all the questions that haven't been answered here, you can go to Ask.Igwin and post the questions, and I'm sure either the mentors or the speaker can get back to you. Thank you, Victoria.
Sorry, Apratim. I received a direct message to enable or turn on the live transcript, but I don't think I can.
Yeah, I'm also having a problem with doing that. So maybe that's...
okay.
Yeah, sorry about that. Yeah, but we will check that. But in the meantime, I think we should move on. So next up is Eric. Apologies if I pronounce it wrong, but it's Eric Chassande-Mottin from APC Paris. And Eric, over to you. Please feel free to start whenever you're ready. Thanks.
Thank you, Apratim. So I will try to share my screen first. Can you see my screen now?
Yes.
We can.
Okay, thank you very much. So yes, you pronounce it right, Apratim. I'm Eric Chassande-Mottin. I'm a senior researcher at CNRS. I'm working in this laboratory called Astroparticule et Cosmologie, APC, which is on the campus of Université Paris-Cité, Paris, France. I'm working on, I'm part of the Virgo collaboration doing data analysis, and I'm also part of the GWOSC team that is the center that is releasing the gravitational wave public data. So this is the subject of that lecture now. So I'll build on what Victoria introduces you just now and elaborate a bit more on the context. So what we'll be talking here is the data from those 5 detectors. So you see the LIGO detectors in Hanford and Livingstone, the Virgo detector in Italy close to Pisa, the GEO detector in Germany close to Hanover, and the Kagra detector in the Kamiokande mine in Japan. Those detectors have been taking data since 5 years. So the LIGO detector started 8 years ago in 2015. And you see the three major phases related to data collection here, which we call observational runs. So you see three phases, O1, O2, and O3, with their duration. You see from few months to a year. And the various detectors, Virgo, Geo, and Cagra, have joined the global network gradually over this period. So during this period, well, we've seen in 2015 the first detection of gravitational wave with in this data, and the events collected by the detector so far, LIGO and Virgo only, have been gradually collected. So you see the various event count depending on the I see somebody is trying to drawing on my slides. That's okay, but all right. Just want to make sure that everything is fine there. So you see the various events collected, and really the rate of collection of event increasing with time as the sensitivity improves, and you see really a real change in the slope of the event collection after O2, and we expect that this will increase even more with the future runs as the sensitivity improves further on. Overall, we have collected about 90 events, and these are composed the so-called gravitational wave transient catalog that I'll be discussing further later. So the LIGO-Virgo-Cagra collaboration is committed to the principle of open science. This means that we have a policy for releasing our data, and this policy is described in the data management plan. This is linked to this slide here. You'll have the possibility to take a look at this document. It describes the way we release the data and the rule we follow to do this release. And the Gravitational Wave Open Science Center, so GWOSC, which is available at this URL gwosc.org, is really the instrument to implement this policy. So on the GWOSC webpage, so you see here on the left here, you'll see releases of gravitational wave data. You'll see event catalogs, so GWTC, and you'll see the required documentation and the software tools that you may need to use this data and to understand the nature of the data. So, right, so this presentation here is really about the GWOSC, and what I'd like to do now is a tour of the GWOSC. And so, as you see, we'll start with what, I mean, the primary function of the GWOSC, which is the availability of the data from LIGO, Virgo, Cagra, and Geo. So you see here on the main page, you have two ways of accessing the data. So this is there on the top menu. You see the get data download, or you can click on this direct button, explore data. And if you do so, you are led to this page, which is actually much longer than it seems here. The list of blocks here extend much to the bottom of the page. And basically what you can get here is access to the observations of the various detectors associated to the various runs, on top of other data release, which I won't have time to really describe here. So let's take, all right. So when I talk about data, I first need to say what data I'm talking about. So as Victoria said, the detector, the interferometric detector here, are measuring the so-called gravitational wave strength, H, that Victoria already introduced. So this is the differential length of my two rulers that Victoria spoke about. And this is a relative measurement. So this is delta L over L. This is something that measures the space-time deformation in a sense, and caused by gravitational wave passing through the detectors. And a bit more concretely and pragmatically, what this means is that this measurement is done during an observation run at any time, okay? And therefore, we are led to a time series, which in fact is sampled at 16 kilohertz. So this is very similar to what you get when, you know, music recording, you have a time series sample at this typical frequency. Well, on CD, it's 44 kilohertz, but you see there is only a factor of 4. And therefore, you could, in principle, put this signal on a loudspeaker and hear what the various detectors are recording in time. So this is really an audio type signal. Of course, this is long observation, typically for several months or to a year, but there are a lot of on and off interruption that when analyzing the signal, you'll have to cope with, right? So this is not a continuous, really continuous, strictly speaking, observation. There are a lot of breaks in there. Okay, so far the available data sets are given in this list here, and by downloading them, what you have is all you need to reproduce the LIGO Virgo Cagra analysis. So if you want to implement your own search, you have a great idea. You simply want to reproduce what the LIGO Virgo and Cagra have been releasing, you can do by downloading this data. So this is what we call the bulk data. So the entire recording from a run. It is available in various formats, and you'll have to use data quality if you want to search for event and signal. So this information is also available along with documentation. So far, three major data sets has been released. O1 was released in 2018, O2 in 2019, and O3 in two parts, A and B, in April and October of 2021. So let's take an example here. So if I click on this 4 kilohertz data button of O3A, oops, I'm going to this page here, which will allow me to access the O3A 4 kilohertz data from access it file by file. Actually, I think it's O3B. I circled the wrong button here. I should have circled the O3B button. This is the page I'm looking at. So you see here on the left, you select the detector. So here I selected Virgo. You select a start time, an end time, the type of output format you'd like, and then continue. And then you're led to this list of files where, I should explain that we in gravitational wave analysis measure time with the GPS clock, which is this long number, something like a phone number, right? 12, 15, 56, 65, and so on. So these are times since I don't remember which date in 1980. We can use UTC, but this is the primary time clock that we are using. So there are tools on the GWOSC website to allow you to transfer this type of time to any other time clock like UTC or whatever. Right, so I'm coming back to my list. I see here a list of files. the files the files correspond to 496 period 4096-second periods of time, sample either at 16 kilohertz or downsample at 4 kilohertz. And you see here this the time period I requested divided into those blocks, and I can access that in HDF5, which is a portable format, file format, or into the proprietary specific format that we use internally in LIGO Virgo Cagra, which is the frame, so-called frame format. For each of those files, you see the last column here is the percentage of data in this 4096 period long. So you see, because the detector are not working all the time and maybe off part of the time in this segment, you don't have always 100%. Moving on. So this was the file by file access, but if you need to access a full run, like you need to download many files, then this way of doing is not appropriate, and we suggest that you use another way of accessing the data, which is available here, large data set. There is a specific block, and you can access those using the so-called CERN VM file system, CVM-FS. And I won't have time to, provide a technical description of this. There is a documentation that explains how to do this. It's fairly simple. This essentially allows you to mount distance disk partition with the data. So the LIGO Cagra partition that can be mounted on your local computer, so that everything would work as if you have the data access like a member of the collaboration. If you are in the US and you work in the US, you can conveniently use that to access the data through the Open Science Grid. This is I think a distributed computing system that is there in the US. And there is a third way of accessing the data through the API, but I'll discuss that later in my talk. So let's go back to the tour of the GWASC. So now I've been describing the scientific data, so H of T, but we searched this data, we found event, and we characterized those events. All these science and science products are available in so-called event catalog. So this is what you get when you click on this event catalog item here. So you're led to this page here, which is a long list of events. So each of those are signals that have been detected in the data and that correspond to a source, usually and primarily, well, those are mergers of compact stars, primarily black holes binaries, but not only. So we have a list here. You'll have detailed presentation about this. I won't go into detail, but each of these is a binary merger where you see a version. I'll come to that next. The type, the catalog in which it has been released, the GPS time at which this event has occurred, and various numbers that correspond to characteristics of the binaries. So parameter estimated from the data. So let me go ahead. So this is, well, what we just saw is really the catalog that is called the GWTC, Gravitational Wave Transient Catalog. But we release, so this is a cumulative catalog that encompasses all catalogs we've been releasing. The catalog we've released, so subset of these catalogs are notable events that are, remarkable events detected and that deserve a specific publication. Okay, so this is the discovery releases. So this is one type of catalog we have. And then at the end of the run, when we collected the observation from the full run, essentially, the big list of events, we assembled those in a big catalog. So we've released so far 4 catalogs, GWTC 1, 2, 2.1, and 3, with various flavors that will be presented later. The catalogs here, each of those catalogs and the cumulative one can be queried through the online catalog query page. Here is the path to access this query. You see here that you can specify a range of various properties of the source, a range in time, and the type of catalog. And you click on submit query and you return a list of events that you can get in various formats. So this is very convenient. And I think this will be even more convenient when the catalog will be much more, maybe few hundreds or maybe thousands of events. We hope that we'll get in the end with LIGO, Virgo, Cagra. So when you start from this list, from this GWTC list, you have this list of events, and let me click on this of this specific event here. So you understand the meaning of this number. So this is the date. Okay, so this is this is the 29th of January of 2020 and this is the UTC time in hours, minute, and second. So this is how we called and we labeled our event here. So let me let me show you what you get when you click on this event specifically. First of all, I want to stress that here I have one version of this event, but I can have multiple versions. And during the tutorial of the workshop, I think you'll have to take care of the fact that you may have various versions of the event. So you're led to an event page, which basically provide you with the description of the data provenance, the type of data that has been used to detect this event. Then there will be another block that is related to the data snippet. So we provide you with a short segment of data centered around the event. So 2 types, 32 seconds, so minus or plus 16, or basically an hour, 86 seconds, so 248 before and after, in various formats, so frame format, HDF, and text format, ASCII types of format. And then at the bottom of the page, there are a description of the way this event has been detected by search pipelines. So you'll have a specific lecture on this. And parameter estimation. So what are the source parameter? And here again, you'll have a specific lecture on this part. You have 2 images here that make a representation of the data, a time frequency representation of the data. This is done through the so-called Q transform. So let me explain what the Q transform here is. So it is often convenient. So what we are doing here is analyzing time series. Okay, this is h of t, and it can be convenient to have another representation of the exact same data, which is in time and frequency. A usual way of doing this is by doing the so-called spectrogram or the short time Fourier transform. So you divide this time series into blocks, and in each blocks you take the Fourier transform and you collect and you form a kind of a matrix, a time frequency matrix that is being represented here, and in which you can have some other view and another. So you see here, for instance, you have a clear representation in which this signal here, there is some, this is not an astrophysical signal, this is an instrumental noise, but you see here that this instrumental noise has various harmonics, so you can have an understanding of the nature of the noise by looking out to this. The Q transform is some kind of a similar representation, but the way it tiles the time frequency plane is different. And the way it does that is represented here on the right. It allows to have a resolution that adapts to the signal in a sense, right? And that is something that goes well with the log scale, in which you can have a representation of very broad band signals. So you can have a full description of the Q transform by looking to this reference here. And if you have a question about this, I'm happy to provide more details. So let's continue our tour, and again with the third and last data we provide that are so-called the timelines. So imagine that you want to start some analysis. You are interested into some period, say during some part of the 01 data set. In 2015, and but you don't know whether the detector was which detector was operating at that time, how much of the time they were on. So this allows you to answer that question. So you insert the data set, start and a stop, and you select the type of data quality. So this is important. The way you do this is by this flag, the detector. So for instance, H1, the search type. So you have more detail about this. This is, for instance, burst or CBC, and the severity of the data quality. So the so-called category. You'll have a description of that later on. Cat 1, Cat 2, or Cat 3, and then you are led to a file that provides you with these time streams of data quality signal, and also this type of plot in which you can understand whether the detector was operating, yes or no, and with which data quality level. To conclude the tour of the GWOSC, let me go to this software item. So as I said earlier, we have an API, a web API that allows the access to the various data I've been shown so far. So the description of this API is described in this page here. You have the address. You can have the full description. This is a small part of this page. And this API is implemented really as a Python client, which is called GWOSC. And during tutorial 1.1, which is the first tutorial that you'll have to do today, which is entitled Discovering Open Data from Gravitational Wave Observatory, you'll have to learn how to use this GWOSC package. You'll see it's very simple and straightforward. This is essential for the remaining of the workshop, where you'll see the difficulty increases. There are many other software utilities that are available on the GWOSC website that allows you to simulate gravitational wave signal, that allows you to analyze the data. You can have a look by clicking on this link that I have here. But I'd like to move to the conclusion now. So I presume that if you are attending this school, this workshop, that you're interested into gravitational wave science, you're maybe looking for gravitational wave data, then GWOSC is your friend. We have 15 terabytes of scientific data that is available freely and accessible through the license, the Creative Commons license CC BY. And there is a lot of documentation and resources available on the GWOSC. One thing that I haven't mentioned is the so-called data papers. So those are publications that sort of collect all the information I've given so far and even more into a paper that you can read. So the last one we have is the one that we have on the right here, on the left here. So this is the data paper that is related to the O3 data that you can access from the archive. if you want to ask questions, if you have questions and send feedback, I think you know already that this WASC activity is linked to this user forum, where you can ask questions to the community of users, where you can have access to experts that can address your questions. So this is ask.egwin.org. And remember that if you use the data, and we hope you do, and you make more science with the data, please remember to acknowledge the use following the instruction that is given on this page. And with this, I thank you for your attention.
Thanks, Eric. Yeah, thanks, Eric, for the wonderful talk. If there are questions, you can just write to me. I actually can start with one question. So the thing is, you mentioned this different sets of events, like the confident, the marginalized, and the auxiliary. Can you explain what is really the auxiliary events?
So I'm not sure I get where are you.
So when you look for, say, GWTC1 or GWTC, I think 2.1,
okay.
you say confident, marginal, and
auxiliary.
Yes.
Okay,
what are
sure.
Auxiliary? Yeah.
Yes. So let me go here. Wait a second. Right, this one. Right. So when we release catalogs, we separate the event and the signal we detect depending on the significance, the statistical significance that are attached to each of the signals. So we have, sort of a convention based on the so-called false alarm rate, which measure some kind of a probability of that event to be associated to the noise, and based on the value of that number, we can either formulate it that this event is an astrophysical event confidently, or the significance may be marginal, and therefore we are a catalog that is a list of all confident detection we are making, and another catalog which collect all the marginal detection that we made. And therefore, these appear in the list as GWTC3 confidence or GWT3 marginal. So that's it. And you need to make sure that to understand really what is the convention, so it can relate to the false alarm rate, as I said earlier, but it could also relate to the so-called P-astro value, which is a Bayesian feature, a Bayesian figure of merit that also includes knowledge from the past detection and a model of the signal population, of the source population.
Thanks, Eric. So sorry, maybe I was not clear. So I'm aware of the confident, the marginal. I was just more asking about the auxiliary one. So if you
of
see
the auxiliary one. Oh,
yeah.
right. Okay. So this one. I'm sorry. So auxiliary means that right. So this is a there are detection during this run here that was O2, that was signals that were identified as confident detection during the O2 run, and that turns out after reanalysis to be not to match the convention for making a confident detection, and therefore we list those as auxiliary because they were mentioned as event earlier in the first trial we did for the analysis, but they are not event anymore in the second trial. But since we've mentioned them already. They are really part of the catalog as auxiliary.
Got it. Thanks. So sorry, I took up most of the time. So there are a couple of questions maybe. So what is the difference between O3A, O3B, and O3GK data release? And can you please go over the reason behind studying the Fourier or Q transform of the data? Maybe Q transform is the interesting question. So yeah.
Okay. So what is the question really about the Q transform?
Basically to go over the reason behind studying the Fourier or the Q transforms.
All right. Well, the reason about using the Q transform is I think it should, you know, make sense already with this plot, right? If you stare at the time series that I show here in this example, you'll have a hard time understanding what is it about. Is this astrophysical? Is this something else? Is this, you know, and therefore you'd like to have some collection you'd like to have some more information about what is really the structure of the signal. And and if you do so, then indeed what you get is really more information. For instance, here you're looking at the Q transform on the right, you'll see that this event that lasts for a couple of seconds have, you know, a number of harmonics that may be, you know, interesting frequencies to which you can possibly go back to some model of the detector and try to understand what is the nature of that transient that we are looking. And similarly, when you are looking at an astrophysical signal, so let me go back to this page here. Well, you know, in this example, you'll see really the chirping type of structure that you expect from a merger, this power law evolution of the frequency in time. And possibly you could see also harmonics, right? Those are very interesting possibilities. There are tentative of analysis of these higher order modes that are predicted by general relativity as well, and that are important tests of general relativity. So you can tentatively expect that you could see, and in fact, I think you can barely see this in some of the events, to see, you know, extra order modes, higher order modes to the signal in those time frequency plots. It will be very difficult to see those in a time series, standard time series. So I think this time frequency representation really does make sense because of the non-stationarity of the signal, either astrophysical signal or instrumental artifacts that we are dealing with.
Thank you. So I think we should thank Eric once again, and for all the questions which weren't answered, you can ask at ask.equin. Thank you, Eric, if you can hear me.
Thank you.
Yeah, thanks a lot. So now I think it's a good time to give Agatha the floor to explain the tutorials. Agatha, please.
Yes. Hi, can you hear me? Hi?
Yes, I can.
Okay.
Yes.
Hi again, everybody. So in these tutorials, in this section of the Open Data Workshop, we always give a small introduction to the tutorial at the end of each day. But since today is the first day, I think I will make a bigger detour of all the technologies that we are asking you to use related to the tutorials. So let's see if I can share my screen once. Sorry, because I'm also sharing my screen with the okay, sorry, I'm using also. Okay, so I hope you now see my screen. So
Yes, we can.
I want to, yes, thank you. I want to start from this website, so that to show you that you can start from one simple string to remember, and from that you can see all you can reach all the material that we have in the workshop. So the fundamental thing to remember is just GWOSC, GWOSC.org, which is the Open Science Center, the website Eric have largely discussed about. So here you can reach the material of all the workshops, including this one, from these windows here. So if you click on workshops, you will reach this page. And again, if you click on the workshop of this year, you will reach, sorry, someone can close the door? Sorry, we are in a study hub at the university, so someone is in the corridor, is very loud. So you arrive, I was saying, to this page, which is the page of the workshop that you should already know. And this is the link specific to this page. When you register, you should have registered here, and this will bring you to a platform that is called Thinkific, this one. Then what I want to show you now is the section tutorial. So you see here there are two buttons. That one online course is again the same Thinkific. Is, as you see, it goes to the same link. So why you see this link here? Because every year this workshop always become an online course. And where you see that's the content of the workshop and of the course. But it's useful even during the workshop to have this page handy, and I will show in a moment why. Now let's go back here to this the page that content of the important links. So I was saying in this section tutorials, you see, so the first link is the online course. The second link goes to Run's tutorial. Run's, this one, will open a GitHub repository. So if you have never seen a GitHub repository, don't worry, it's a very easy thing to handle. We have done the work for you to put together everything and put together a README that you can easily read, and from where all the links that are useful for you can be found. So, for example, you should have already seen hopefully this page that is called the setup, software setup. I think so. I'm the one that always send all the email and I've to the participant to the course. So you should have already received an email last week saying, have a look at this page. That was the page. And I'm here just to show the different options you have when you want to run the tutorials. So the first one is the easiest way. So Colab is a way to run the tutorial online without any local installation. And I will show this in a moment how it works. Then the second option is My Binder, which is another way to do the same, except that this takes longer. So I suggest, if you don't want to install locally, to use Colab, but we put this option here to have an alternative, because some operating system can cause some trouble. So it's good to have, even if it should work for any operating system, but it's good to have an option. If you want to use My Binder, the only warning is it takes several minutes to load, because it creates like a Docker image and then it runs the tutorial inside there. Then the last option is basically to use Conda. So to use to install locally in your machine a Python virtual environment. This is called Conda. Then this is, you see, is a bit longer because there are all the instructions these are all instructions that have to be brought in a terminal. And if you have Windows, you can do the same, but the same Conda installation. But first, you have to install a Windows subsystem for Linux. So that's just to give an overview of this page. So now I want to let you see what happens when you open Conda. So I click in this open in Colab. So when you open this link, you arrive to this page of Google Colab. So where you see this is the name of the GitHub repository, this is the branch, and this is the name of all the tutorials. So let's start with I will show in a moment the tutorial of the first day. I want to, since I'm here, raise your attention on this tab. So there is, you see now I'm in the tab that is called GitHub, which and it goes there by default when you open Colab. But there is also a tab called Google Drive, and if I go there, you see these are some my local version that I've saved on Google Drive of the tutorials. Because what will and I will show in a moment why I'm highlighting this, because when you open the tutorial and you try, you can modify it, but but you cannot save locally. What you can just do is copy to the drive and then save from there. So before going to this tutorial, another thing I want to show you, going back to the home page of GitHub, in this folder that is called tutorial, you see, so there are different, you see day 1, day 2, day 3. So for each day, we have picked a list of tutorials that we think they are appropriate for the lectures of each day. So the tutorial of today are about this topic. We have seen this morning how the detector is done, and how the WOSC website is done, which data are available. So the tutorial allows you to discover the data and use the WOSC packages, the WOSC package that the API that Eric mentioned in the introduction. And beside WOSC, the other package you will learn to use is this one that is called GWPy, that is used to download the data, to plot and manipulate the data. Okay, and so when you go to this folder, you see that there are 4 tutorials. The first one, that it's the one that I've opened in the other tab, is about the data, then so the package WOSC. Then the second one is about the other tutorial use GWPy. So the first one is just to access the data, and the third allow you to do the Q-transform, and then the fourth tutorial explain how to generate waveform, and for that you will use another package that is called PyCBC. Okay, so now let's go again to the tutorial that I've opened here, because I want to give you some other practical information that can be useful. So each tutorial is organized in this way. There are, so if you have never used notebooks, don't worry, they are very easy to manipulate. You see that there are some cells. Each cell can contain text or code. So these first 2 contain just text. And when you see something that is in gray like this one, this is a cell that contains code. To run each tutorial on Google Colab, you need always to uncomment this first line, because you need to locally install a specific package that is needed for the tutorial, while if you have installed Conda locally on your laptop, or you have launched My Boundary, you don't need to uncomment that, because these packages are already installed. But if you are on Colab, which is what usually most of the students do, you have to run this cell. So when you open this cell, you always have this warning. Don't worry, you will you can click on run anyway. And by the way, you see my face here because you need to log with an account. Anyway, so you see this thing going here around the bullet means that this cell is running. And then, so now I have installed locally, and I can check that it worked by running this other shell. And now I see what is the local, the version that I've installed locally. So then again, when you continue to run the notebook, you always see some text, some code, and so on. You can run all the cell in this way with run all or restart and run all. And but you can launch them one by one. What I want to say is that you can also add, for example, a cell with some code, and then another important feature that can be useful is that you can ask in the information about the method with a simple with this syntax. So you can either run this cell, or directly you saw when you pass the mouse there was already the help. So so if you copy the method that you are using and you put a question mark, you see all the help with all the description of the method. Okay, anyway, so what we ask to do is to read this, to run this code, add some cell to play with this code to understand what's happening. And then at the end of each of this tutorial, you have some exercise. So to run this exercise, you can write your text here and run it. All the exercises are always are meant to be run with the same code that you have below in the upper part of the workshop. So you read carefully, understand what it says, and then run it. Then once you have done your exercise, what we suggest to do is go again on this Thinkific platform, so where you have already registered, and sorry, I have to sign in. Just a moment, and sorry, oh my God. Perché? Sorry, I have just to open my verification code so that you see that this can happen, and it's very easy. You just receive an email with the code. So you can go to, you will see a different visualization than mine, because I'm a manager, so I see different things. But what you see is something like this. So that's the version that you see, that was also Apratin was showing. But what I want to say is that here you have the activity for all the tutorial, and you have the same question that was at the end. You see how many months or to last, and then here is the same. Then what I suggest you to do is do your calculation, write your code, go and reply to the question. When you reply, you will ask to confirm, and then you always have this output. So you have you will have the reply, the answer is wrong or right, and then you have some hint of the code that you can use to reply to your question. So even if you are alone, you are not in the study hub, you have all the help that is needed to run this exercise. And I suggest you to always run the exercise, not only to understand if you have run your exercise correctly and to give hint on the reply, but also for us to track down what's happening if students are on with the hands-on. Then the last thing I want to say, we have vastly spoken about ask.egwin.org. So that's another link that you should keep in mind. And we have said you to post your question here. I've sent the link about where to put the question about each day, each tutorial, but as you can see, you can easily reach it. So I see that already there are questions about the tutorials. Another thing that I want to say is that we are using this platform because there is also this search possibility. So, for example, last year there were a lot of questions about the Q transform. Sorry. And for example, if I search for it, I see that there were a lot of questions last year about that. So you can have a look. So before asking your question, you can see which have been the replies in the previous years to this question. Because, for example, the Q transform is one of the topic that is always problematic. So, for example, you see that there is a thread with no, this is from this year, but there were also from other years. Okay, and I think that's all. The last thing I want to say is for all the ones that are hosting a study hub, I sent around this message. You should have received a notification. So we ask all the ones that are hosting study hub, please take some picture and have a look at this survey where we are trying to collect the number of people that attend each day. This is very useful for having statistics and study the attendance of the workshop. Okay, I think I said everyone. The last thing I want to say is that when you finish all the online course, you will see a pop-up in the upper part of Thinkific that allow you to download a certificate, an attendance certificate. And sorry, it seems that you cannot see my screen.
I was able to see your screen. I was able to see the ask.egwin screen before. Were you there? Did you switch to some other screen?
No, sorry, I saw the other tutors that are here are telling me that there was a problem with Thinkific, but I'm not sure I understood which was the question. Can you say that again?
No, you were talking about the screen share, so I could see the ask.egwin page that you shared. So if you were sharing something else, then I'm not sure, but yeah, the ask.egwin.
At some point I was sharing a page of Thinkific, this one. You can see that?
Now I can, yes.
Okay.
Yes, this was not visible before, yes.
Ah, okay, sorry. Okay, so I don't know. I think I said everything there was in my mind. I hope all the instructions are clear. I don't know if the other mentors, host, organizer want to add something.
I have a couple of things to say at the end, but if Simone wants to say something, because I don't see Greg here. Simone, do you want to say something or go ahead? I actually don't see Simone. Okay, sorry. So let's take this opportunity to thank all the speakers. That's first thing. Also, as Agatha mentioned, people who are joining in-person study hubs, great, please do. And take pictures, enjoy the tutorials. Those who are unable to join any in-person study hub, we will keep this Zoom link on and we will come back for the tutorials in half an hour. But this is not going to be streamed online, on YouTube. So if you are in this time zone and if this time is favorable for you, you can, we will come back around half an hour from now and you can join us. So we have some in-person study students here, participants here, but we can also keep this Zoom link on. Yeah, sorry, Agatha, you want to say something?
Yes, no, because I received a question, maybe it was not clear.
Okay.
Maybe it was not clear what I meant about Thinkific. So Thinkific is meant as a place for you to get to check that you have done the exercise correctly, and then you can post the reply to the questions that are on the tutorial there. There is no, you cannot digit. You can just say the question correct is A, B, or C, and then you get an help. So it's not that we check if you have done the exercise correctly, if you have copied from Thinkific, if you have copied from your neighbor's meant. What we want you to learn, so we are not the police, we will not want you to send us your code that you have done correctly. No, what we are here is just to help you, and we want you to learn. So do the exercise honestly, and then go in Thinkific and put the reply to the questions. If it's correct, good. If it's wrong, you will have the answer. You should have done this way, so that for you to learn. And then one thing that I forgot, I think for the tutorial of today, all the questions are on Thinkific, but in the next day there are tutorials much more complex that are, and also the exercise. Some are simple, some are more complex. The one that are, let's say, more complex are marked as optional, and those does not have the equivalent on Thinkific, because we ask you just to do the simplest thing. But if you want to do also more complex exercise, please do. We have provided questions for that.
Right, thank you. So also to find out where the study hubs are, because I'm getting some questions about study hubs, you can go to Ask Igwin and find the study hubs where they are. So I just want to answer one question. So there is a study hub in Bangalore. This is at ICTS, and it's going to be tomorrow and day after. So you can join there and find out more options about that.
Yes, yeah. So if you want, I can share again my screen. Sure. To show how the study hub can be found. So again, if you just start from the simple WOSC.org, so no one get confused, and from here you go in workshops and then open the page of the workshop. There is here this button that say find the closest study hub. You can click there, and another ask.igwin.org page open, so you can read all it's written here, or you can open this interactive map that show the location of all the study hub, and for each one you see there is another a link that goes specifically to the post in the same page with all the instruction to reach the study hub. So, by the way, I'm impressed by the geographical distribution of all the study hub. And that's okay, sorry.
Okay, thanks, Agatha. So, and we have like crossed time by 15 minutes, so I think it's a good time to stop. So we will go offline from YouTube, but this Zoom link is going to be alive, so you can come back in half an hour. So there might be like a delay of 5-10 minutes, but we will start the tutorials here. But this is based out of Ayuka, and yeah, so there are some in-person participants, but we will keep this Zoom link on. Okay, thank you. Thanks, everyone.
See you tomorrow.